Hello guys, welcome back to another video on my channel, Gamma Die Gamma. In this video, I'm going to actually prove Ramanujan's master theorem. It is actually a direct application of the theorem of Mellin transforms and the inverse of Mellin transforms. And it's a very nice formula. It's a powerful formula. It's called a master theorem because the integral and the relations it gives actually helps us to derive many nice properties and prove and evaluate many different types of integrals. So let's get started. I won't go through the examples in this video. I will prove the theorem, maybe talk about the implications, the assumptions that the theorem needed and how we can weaken them. And I will try to do the examples in a fresh video. So let's get started. First of all, let's recap what the Mellin inverse theorem is. So assume capital F of S is analytic in the strip A is less than real part of S less than B. This condition may not always hold. We just need to find the real part of S such that the integral, because capital F of S is going to be a Mellin transform of some function small f of S, f of x. We just need to ensure that that S makes the Mellin transform integral converge. Now, in this case, we're saying there's a strip such that the real part of S is between A and B. And then we can define f, small f, by f of x equals 1 over 2 pi I, integral from c minus I infinity to c plus I infinity, capital F of S, x to the s minus s ds. Now, this almost looks like the inverse transform of capital F of S, but the condition for this to be the inverse, the Mellin inverse, is that the integral should converge uniformly and absolutely for C in A and B. Then, and only then, we can say that this is the inverse transform of capital F of S, and then capital F of S is the Mellin transform of small f of x. So capital F of S is integral 0 to infinity x to the s minus 1 f of x dx. And as I said, we may not always have a strip, a convenient, nice choice of a strip like this. Sometimes the real part of S, the region of convergence of the Mellin transform, is on an unbounded region. And that's fine as long as we can make such a choice and then have the C, which is between A and B, the C, which is, is going to be the real part of S, basically. As long as that family or that choice is such that the integral converges uniformly and absolutely. That's all we need. Okay. Please watch the previous video if you haven't, understood this properly, or feel free to write me in the comment section. Let's move on to the theorem for today. It's Hardy-Ramanujan theorem. This is actually a proof of Ramanujan's master theorem by Hardy because Ramanujan wasn't formally trained in proofs. It's a very nice proof. It's well constructed. You can see that all the conditions, the assumptions that we have are going to be utilized. Nothing is actually gone for waste. I'm going to run you through which assumptions we're going to use when and why. Let's go through the statements first. Let phi of z be an analytic single-valued function. Means there's no branch cuts and all sorts of things like that. Defined on a half plane. So it's analytic on a half plane. H of delta, which is the set of all complex numbers z belongs to C, such that the real part of z is greater than or equal to minus delta. For some delta that's greater than 0 and less than 1. So delta is just some parameter. It's not some, analysis kind of, there exists some delta. Delta is just a parameter. Suppose that for some a, capital A less than pi, phi satisfies the growth condition. Absolute value, or in this case a modulus, phi of v plus I w is less than c times e to the pv plus A times modulus W for all Z equals V plus IW belonging to H of delta, where C, P, and obviously A are just constants. Then for all real part of S greater than 0 less than delta, we have the following integral from 0 to infinity x to the s minus 1, and then we have an infinite series of sum of phi of 0 minus x times phi of 1 plus x squared times phi of 2 minus so on, which I can write as sum from k equals 0 to infinity minus x to the k phi of k. I have that equals pi over sine of pi s times phi of negative s. That's the theorem. That the theorem guarantees this integral identity like this for some complex function phi satisfying a certain growth condition and a bunch of these properties of being defined and analytic on the half plane delta with the growth condition. Okay, let's do the proof. Let x be such that x is greater than 0 and less than e to the minus p, and c be such that that's greater than 0 and less than delta. Let's just check first of all, because this sum is going to be inside the integral. Let's just first check that the sum converges, otherwise the integral doesn't really make sense. So to check if this converges, the sum from k equals 0 to infinity of minus x to the k phi of k, we can check convergence by the root test. So what that means is take the nth term of this the nth term of the summand here, which is going to be minus x to the n phi of n in absolute value to the nth root, which just is the nth root written like that, which is basically power 1 over n, and then take the limit as n goes to infinity. If that limit is less than 1, then we know that the series converges, and that indeed is the case, because if you use the growth condition, so first of all we know x is less than e to the minus p, so we get e to the minus pn, and then if we use the growth condition assumption for the phi of n, well, we see the parameter here is going to be n, and n is some real number, so we don't have the a term, we just have the pn term, c times pn. That is going to cancel with the x, because the x gave us e to the minus pn, this gave us a pn. All we have is that constant c raised to power 1 over n in the limit as n goes to infinity, and that is indeed 1. So this entire thing is less than 1, and the infinite sum converges. Fair enough. So the problem is really well defined. The growth condition, we have used it once and we're going to use it later as well. Let me just illustrate quickly what the region of analyticity is for the phi and phi of z function. So as I said, it's the half plane defined such that the real part of z is greater than minus delta. So well, minus delta is between 0 and 1, so minus delta is between minus 1 and 0. So the real part of z is greater than minus delta. So it's all the values of z, all the values on the real axis that are greater than minus delta. So this is basically the shaded, whatever I've shaded here in these slanting lines, that's basically the region of analyticity or definition for our phi function. This is just a nice illustration for you. We're not really going to use much of this. This is just for a visual cue. What we actually are going to use though is this contour that we're going to integrate on. So the contour, which I will call capital gamma, consists of this vertical segment from c minus I infinity to c plus I infinity. That should tell you that the center of this semicircular contour, the center about which we have the semicircle, is c, and c, as we know, is a real number that's between 0 and delta. So that's pretty good. And the radius of this semicircle is going to be capital N, and I'm going to set capital N to be some natural number. It doesn't matter we're going to take the limit later anyways. The closure, the semicircular closure on the negative, on the left side of the real axis is I'm going to call small gamma. So let's first tackle that, because that usually goes to 0, and it will in this case as well. So absolute value I sub gamma is going to be integral over gamma of what function? Well, the function we're integrating is pi over sine of pi z times phi of minus z x to the minus z. So instead of g, I think there should be a phi. Sorry for the confusion there. Okay. Yeah, so that's the function. So we have absolute value integral over gamma pi over sine pi z phi of minus z x to the minus z dz. And then we're going to take the natural substitution in this case to be, well, actually, it's going to be c plus n times e to the I theta, where n is, at the capital N is, as I said, a natural number. So that's fair enough. Then the bounds of integration are from pi to 3 pi over 2, because we're going from pi to all the way around to 3 pi over 2. Pi times phi of minus c minus n times e to the I theta x to the minus c minus n times e to the I theta divided by sine of pi times c plus n times e to the I theta ni e to the I theta d theta. This is just substitution of the new variables. And then we can use the triangle inequality for this integral to get integral from pi over 2 to 3 pi over 2 c times capital N times pi times, now using the growth condition, e to the an absolute value of sine theta. With the growth condition, the p part cancels out. So all you have, because this is now a complex argument for the phi, e to the an times absolute value of sine theta divided by sine theta absolute value of sine theta time of pi times c plus n times e to the I theta d theta. Now let's just focus now for the denominator, because now we have absolute value of sine of pi c plus pi times n times e to the I theta, which I can write as sine absolute value sine pi c plus pi n cosine theta plus I times pi n times sine theta, which for which I can use the compound angle formula for the sine of a plus b. And wherever I have this imaginary angle coming in, I'm going to replace that either by a cosh or a sinh. So absolute value is sine of pi c plus pi n times cosine theta cosh pi n sine theta plus I times cosine of pi c plus pi n cos theta times sinh pi n sine theta, closing the absolute value off as well. But now we have a complex number, and the modulus or the absolute value of that, we're going to have a square root of the real part plus imaginary part. So square root sine squared pi c plus pi n cos theta cosh squared of pi n sine theta plus cos squared pi c plus pi n cos theta sinh squared pi n sine theta. Write cosh squared of pi n sine theta as 1 plus sinh squared of pi n sine theta. Write cosine squared of pi c plus pi n cos theta as 1 minus sine squared pi c plus pi n cos theta. This is just the square identities for the hyperbolic and circular functions. In the end, we get absolute value of sine pi c plus pi n e to the I theta to be square root sine squared pi c plus pi n cos theta plus sinh squared pi n sine theta. So all the cosh and the cos parts just vanish because of those identities. And that is greater than or equal to sinh of pi n absolute value sine theta. Well, we actually want whatever we have here in the very end of this inequality to be positive if the argument is positive, sinh is positive. So that's why I've just taken the absolute value inside the argument. And that sort of bodes well because, we had an absolute value of sine theta on top in the original I gamma absolute value. So I gamma absolute value less than Cn pi, integral pi over 2 to 3 pi over 2 e to the an absolute value sine theta divided by sinh pi n absolute value sine theta d theta, which actually can be expressed, sinh can be expressed as 2 in the denominator, 2 over e to the pi n divide absolute value sine theta minus e to the minus pi n absolute value sine theta. Everything else is the same. Now, we want to take the limit as capital N goes to infinity. So for that, we need to argue by the dominated convergence theorem. Notice the integrand that we have. And I'm including the n as well because, we have to argue for all n. That's the limiting variable. Is upper bounded by e to the theta squared, which is Lebesgue integrable in theta for, whatever domain, whatever range of integration we have. So, by dominated convergence theorem, and again, this is a little bit of this is a sketch of the argument you would do. You can take the limit inside the integral, and then we notice that this quantity entirely goes to 0 and this is where the a is less than pi condition comes in, because when you divide everything by the numerator, if you divide the numerator and denominator by e to the an absolute value sine theta, you see you're getting a factor of pi minus a times n times absolute value sine theta in the first term of the denominator. And you want that to be positive. You want pi minus a to be positive. That means a has to be less than pi. Otherwise, you won't be able to compete with the n in the numerator. That's also going to infinity. If that were negative, if the exponent had a negative argument, if a were greater than pi, you wouldn't really have that. This would blow up to infinity because of the numerator. It's because a is less than pi that we can actually challenge the other factor that's in the numerator, the n, to give us 0. Fair enough, that's done. Now all that remains to be done are the poles and the residue theorem. So the poles of f of z, which is pi over sine pi z times phi of minus zx to the minus z. Let's break it down. Let's look at individual functions. Well, x, we have 1 over x to the z, right? That has poles at z, x. Well, we don't want poles in x. We want poles in z. That really doesn't have any poles. So it's out of the question. Sine, yes, sine does. We want to find poles in z, not x. Well, we're going to have poles for all integers. So z equals k, where k is some integer. But the ones that are enclosed are actually going to be z equals minus n, where n is some natural number. So we're going to have poles minus 1, minus 2, minus 3, so on. Because those are the only ones that are enclosed, because our contour is on the line C, which is between 0 and delta. And delta is less than 1. So the only kinds of poles we're going to enclose in our contour, which has a left side closure, are going to be the negative natural numbers. So phi of z is analytic on the half plane edge delta, so whose real part of z is greater than minus delta, for delta between 0 and 1. So phi of minus z is analytic on z belongs to complex numbers such that the real part of minus z is less than delta, just flipping the inequality, which is less than 1. So as long as we're less than 1, we're going to be analytic for phi of minus z. So phi of minus z is analytic over z equals minus n, because minus 1, minus 2, minus 3 are all less than 1. So we're not going to have any overlap between the poles of phi of minus z and sine of pi z. And also, we're not going to have any individual contribution of poles from phi of minus z, because the contour encloses no poles, because the c is between 0 and delta is less than 1. So, our placement of c is such that it's less than 1, is less than delta, is less than 1. And that's why we're pretty much analytic throughout, and even when we do the closure on the left side, we're still going to satisfy this. We're still going to be in the region of definition of analyticity for phi of minus z. And that is, using all the assumptions. We use the a less than pi assumption in the closure argument. We're using analyticity here and for the sign. And we're actually arguing why we chose c to be less than delta. It's because so that we don't run over the poles of phi of minus z and neither the sign. Okay, moving on, the residues is a simple calculation. The only kinds of poles are for the negative natural numbers. So let's do for an arbitrary negative natural number, and we're going to anyway sum over them. So limit as z goes to minus n. The calculation is going to be pi times z plus n phi of minus z x to the minus z over sine of pi z, which I can rewrite as, let's see, pi times limit as z goes to minus n, z plus n, and I think I'm going to need a phi of n, or we can just say minus z because we still have to plug in the limit. Well, since phi doesn't have any poles anywhere, it's analytic wherever we're, doing the limit and the contour and the closure. We can just substitute that in without having any changes. So pi times phi of n, limit z goes to minus n, 1 over, we're doing L'Hopital's rule now. So the numerator just, is 1, differentiating with respect to the z. ln x, x to the z, sine of pi z plus pi times x to the z cosine pi z, which when we plug the limit in just becomes pi times phi of n times 1 over pi times minus 1 to the n x to the minus n, can be rewritten nicely as minus 1 to the n phi of n x to the n. So by the residue theorem, we have 1 over 2 pi I, the integral, because the only part of the big gamma integral that remains, the closure went away. Let me just go back. This small gamma closure just went to 0. We showed that. Nothing else really survives. It's just this this vertical integral from c minus I infinity to c plus I infinity for the appropriate choice of c bit that's between 0 and delta. So that's why we have 1 over 2 pi I integral c minus I infinity c plus I infinity pi times phi of minus s x to the minus s over sine of pi s ds is actually, by residue theorem, we know what the value for the residue is for 1n. We're just summing over all of them. So sum from k equals 0 to infinity, minus 1 to k, phi of k, x to the k. Now, the function f of z equals pi over sine pi z phi of minus z is analytic on 0 less than real part of z less than delta, because we can just see that clearly. Delta is less than 1, and if we're between 0 and 1, we're not gonna really be touching any of the poles of the sign, because for the sign to have poles, z has to be an integer. And we're clearly avoiding the integers, right? We're less than 1 and we're greater than 0. There's no integers between 0 and 1. And we're also less than 1, real part of z less than 1. Or in this case, real part of minus z less than 1. So we're also not going to run into any poles of phi of minus z. That's why the function is analytic everywhere on 0, less than real part of z less than delta. The integral converges uniformly and absolutely for c belonging to ab, and 0 is less than a less than b less than delta, because again c has to be less than delta, right? So a and b are such that we can place the c anywhere in between them, because b is less than delta, therefore c must be less than delta. So that's just like a convenient kind of range that we have. And again, all of this depends on having that strip. Then we can conclude by the first recap Mellin inverse theorem that I mentioned, that the Mellin transform of this infinite series, so the Mellin transform is integral 0 to infinity x to the s minus 1 sum from k equals 0 to infinity minus 1 to the k phi of kx to the k dx is just going to be, so the Mellin transform of this sum, infinite sum, is going to be pi over sine pi s phi of minus s for all real part of s greater than 0 and less than delta. Why? Because that's where this function is analytic, and also that's where our integral will converge. That's where the inverse will also exist. So as long as we have found a value, a real part of s that makes the inverse converge, that's also going to be the region of convergence for us. And that's the proof. This is basically what we wanted. Now, this is not the standard form you might encounter on Wikipedia or on other literature sources. So what they do is we have phi of u, substitute that as lambda of u divided by gamma of u plus 1 with the appropriate conditions on lambda of u. So what that means is we have conditions right now on phi of u. Just convert those conditions, plug this form, this substitution, lambda u over gamma of u plus 1 into that, and get analogous conditions for lambda of u. It's not too hard. You just have to account for this gamma function in the denominator, that's all. So get a growth condition for this and everything. And so that you're reformulating the theorem in terms of lambda of u instead of phi of u. And when you plug that in, your entire calculation and also the final result, and your range would also change. Your region of convergence would also change to accommodate that substitution. You would end up with integral 0 to infinity x to the s minus 1 sum from k equals 0 to infinity lambda of k over k factorial, when I'm writing gamma of k plus 1 as k factorial, minus x to the k dx is actually gamma of s times lambda of minus s. This, where did the sign and everything go? Because of the gamma function reflection formula. That's what happened. That's all that is to it. And this is the well-known Ramanujan master theorem formula. He formulated the master theorem in this form first, using natural assumptions in quotes. Again, that wasn't rigorous, but it so happens that the conditions that we have used here can be weakened, and even Ramanujan's in quote natural assumptions are not the weakest. You can go even more weak. So that's why when I do applications, I'm not going to be looking whether the phi of u or lambda of u actually satisfy any of these the conditions, because the conditions keep changing, and if it works, it works. So I'm going to take a more heuristic physics kind of approach to whenever I'm doing the examples and applications of the Ramanujan master theorem. There are two more proofs of this, one by Ramanujan himself using the in quote natural assumptions, where he uses Fourier series, and we are supposed to assume that we can interchange the integral and the sum under these natural assumptions. There's one by an operator kind of increment kind of approach, which again lacks the rigor that the proof by Hardy does, definitely. But there's a certain industrial feel to this proof, because you're introducing all these conditions. You're saying x is less than e to the minus p. You're basically forcing all these things to converge nicely, and forcing all the theorems like the dominated convergence theorem and the residue theorem and the Mellin inverse theorem to sort of work hand in hand with each other. But I think that's the best result, most rigorous and channel worthy proof I could find in literature. And again, when I talk of the strip and that existence of that narrow strip, we can actually extend that using analytic continuation to the negative parts. And that's actually what I explained in the Barnes lemma videos, that we just have to avoid the basic poles of the gamma function. The gamma function is meromorphic. It has the only poles it has are simple. So as long as we just keep avoiding them, there shouldn't be any problem. We can even extend it to the real part of z less than 0, to the negative real plane, where the gamma function is extended by analytic continuation using its functional equation. So I will end my discussion here. I hope you enjoyed the video. I'm sorry if there was a gap, there was a lapse in understanding, and jumping steps, and just let me know if you have any questions. In the meantime, stay home, stay safe, and keep doing math. Peace out.